We turned into
So we need to go to it. I did.
All right. Electromagnetic induction. Okay. So, magnetic flux, we talked about this. It's pretty much the same as electric flux, except it's magnetic field instead of electric field. You're looking at what I would consider the perpendicular component of your area. If you don't consider that, you're like the way I don't do this correctly in a mathematical sense. Like the area I think of is the plane of that. Technically, mathematically, the area vector is orthogonal to that area plane of the area. Hence, that's why it's a dot product. So technically, you find the component that's parallel, but the way I think of it is the component that is perpendicular. It's in Weber's. Is the flux. Okay. Magnetic flux. Weber. And that equation is on the equation sheet. They have a B. So, okay. And actually, it's on the equation sheet, they have this. That's what they have on the equation sheet. Okay. Good with that. Okay. And we actually did an example with that, one of those free response problems on the board the other day. Good? Okay. All right. So Lenz's law. Um, this is saying it's more of a conceptual idea. This is if there is an induced current in a loop, then the magnetic field that is created by that is in opposition, is in the opposite direction of the change in the magnetic flux. That's a mouthful. I'll demonstrate that. It's just easier. I'll show you and you'll like, okay, I get it, rather than trying to memorize that. Okay.
Is that B on the first one, like subscript or variable?
This guy, subscript, magnetic flux. Okay, so Faraday's law. This is the rate. So like knocking out the n and the negative sign, the rate of which your magnetic flux is changing is equal to your induced EMF, your induced voltage. Okay. The negative sign, that's there because of Lenz's law, and we'll talk about that. Okay. The N is just the number of loops, so if you have more loops, you get more induced voltage. Okay. Now, because the flux is dependent upon two variables, and both of those variables could possibly change, to do this, you got to do, what's the name for that? Not the chain rule. Product rule? Product rule. Okay. So typically, I've not yet seen this happen. Usually one of these expressions is zero. Either the magnetic field staying constant and you're changing the area, or the area is staying constant and you're changing the magnetic field. Okay, but this would be the complete version if you had both of them changing, which I think, again, I'm not seeing that yet. But I've also not seen an accelerated reference frame on the test, other than elevators. Okay. Good there? Okay. Give that one a shot.
I think it's like halfway between yes and no.
The field is coming. The field is coming out of.
Hey.
It was just areas instead of circles.
Yeah.
Angle between them. The effective area. The projection.
Correct area is yes. Yes, it is changing because the area is changing. Okay? You are changing. I think I did this already, right? So, like, here's the area. Did I do this with electric? Like the, okay, how much wind is going through here? As that's changing, how much wind can go through that area is decreasing. Maximum flux, minimum flux of zero. Good? Okay. All right. I'm going to walk you through this one. This is the Lenz's law thing. You can read it, and then I'll walk you through it. Okay. Just real quick. If you got 7 meters a second going this way, and then sometime later you have 4 meters a second going this way, what is the change in velocity? 3 meters a second going that way. Right? Does that make sense? Okay. So here's how you do these. Step one is you take your left hand and you stick it in the direction of the magnetic field. Okay? That is the direction of magnetic flux. That's your left hand. We're just using this as a place marker. Okay? Now, what we really care about is what's happening to the change in flux. Because the magnetic field is decreasing, the change in flux is going to be, the direction of that is going to be out of the page. Okay, good with that? That's the direction of the change in flux. The magnetic field that is created by the current that's going around that ring is in opposition, always in opposition to the change in flux. So you stick your thumb of your right hand in the opposite direction of your left hand pointer finger, and the direction of the current is in the direction you're curling your fingers around the loop. Okay? Clockwise. Okay? I'll walk it through again. Ready? Once you get good at this, you don't need your left hand. You're just like boom, 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 clockwise. Okay? So, direction of the flux is the same as magnetic field into the page. What's happening to that flux? It's decreasing in this example, so the direction of the change in flux is in the opposite direction. That's why I brought up this example here. Okay? The magnetic field that's induced by this current that's created in the ring of wires in opposition to this change in flux clockwise. So, yes, that's Lenz's law. Okay? You did this last year, absolutely. Okay? That's this in words. What we just demonstrated was that in words. Okay? Good? Try that. Okay, tell your neighbor. Show your neighbor.
Point in the direction it's increasing.
So point in the direction. Point in the opposite direction of flux.
That's how it's gonna work for me.
This goes in. If I'm moving the opposite direction.
Okay. The flux is going out of the page. The flux is decreasing because you're decreasing the area. So the change in flux is going into the page. You're sticking your thumb of your right hand rule in opposite direction of this, counterclockwise. You know what? If it gets to the right answer, go for it. Okay, give that one a shot.
Mr. Smiley, is this all like the opposite direction if you're in Australia? Oh, that's much backwards. Yeah, that's what I was thinking. Because like the toilets go the other direction, surely this would too.
It's just no. Okay, correct answer is flux is coming out of the page. Okay, right hand rule number 1. Okay, current is increasing, so there is the change in flux is going out of the page clockwise. Yes. Okay. Next question. Tell your neighbor. Okay, correct answer is. Correct answer is C, nothing. However, okay, check this out. There is an induced voltage, but does not produce current. Okay, you've got a conductor. Ooh, sorry. I'll retract that. It's true. We're just not there yet. Sorry, I jumped the gun. Okay, give that one a shot. Correct answer is good. Okay. The flux is decreasing because we're taking it out of the magnetic field. Okay. So if you want to do like here's how I do it. Stick my thumb in the direction of the magnetic field. That's our original flux. And then it's decreasing, so I flip it. And then I flip it again for Lenz's law clockwise. Sure. Yep. So, step one, direction of the magnetic field is the direction of flux. Step two, in this scenario, the flux is decreasing. So the change in flux is going this way. Lenz's law says that the magnetic field that's induced because of the current going through this wire is in the opposite direction of this change in flux. So magnetic field in this loop is creating a field going this way into the board clockwise. I'm done. You have been the whole time. I just did my left hand. I was like, this is this way, and then it's decreasing, and then it went that way. I was just showing you how to do it with one hand. Yeah. Okay. Next question.
Give me a second here.
This is anything.
I'll make survey says.
I mean, like, yeah, but I don't know why.
The field is increasing this way, which means
This way, this increasing that way.
Have a conversation.
Because it's on the outside. So it's on like the looping bit, not the right? But because I think it's B is probably. Oh wait, there it is. I thought it was like that kind of. The picture was unclear, so it's on my wall. I don't even know how it was.
Why are we flipping our hands sometime? Again, when it is
So if always,
So why wouldn't we flip our hands again?
because sometimes the flux is increasing and we don't flip it twice. We flip it once, and if it's decreasing, then we flip it twice. It's the change in.
Yeah.
So we identify the direction of the flux, okay, and then and then more importantly,
So the induced field is
yep,
No, magnetic field.
yep,
Okay.
yep,
Okay. Okay, we're there.
okay. All right, correct answer is A. Okay, the field is going out of positive. No, bad. Oh, that was horrible. Out of north into south. Okay. So as you're doing that strengthen. This is getting a stronger magnetic field. Okay. So it's going. The flux is going this way. The change in flux is going this way. So you oppose that. Good. Okay. Transformers.
Is it DC battery or AC battery?
It's a DC battery. It's a battery. I don't think there's a such thing as an AC battery. Have a conversation.
But when it's left on, the magnetic field is increasing.
Only when it's turned on.
Why would it not be?
When there's a steady current, why would the magnetic field increase?
But it says when it's,
Why would you say C?
Correct answer is. Correct answer is A and C. E. Okay. So it is only when the